Thank you for joining us. We're pleased to host you for today's presentation on challenges with controller tuning and process optimization. Our presentation follows the article published by Control Station titled Rejected, the Top 3 Misconceptions of Manual PID Controller Tuning. At this time, I ask that you please put your phones on mute. If you have questions or comments during the presentation, please use the WebEx messaging function. We will be monitoring that. My name is Dennis Nash. I'm the president of Control Station. I'm the principal cheerleader of both our award-winning optimization technologies and our expert team of process control professionals. I'm joined today by Damien Monroe, General Manager of Control Station Limited, and today's presenter. Damien is a veteran he's a practitioner with experience in a range of industry sectors such as oil and gas, pharmaceuticals, food and beverage, semiconductors. He leads the company's efforts within the European region. Today's presentation will follow the agenda shown on your screen. We'll begin by exploring 3 common misconceptions associated with the tuning of PID controllers. We refer to those misconceptions as habit, thrift, and failure or unsuccessful experiences. After covering these 3 areas, Damien will share various industry case studies to highlight the changes in software that enable tuning of complex process control systems. And as time permits, we'll conclude the WebEx today with a question and answer period. So previously referenced as habit, thrift, and failure, the 3 misconceptions of loop tuning are grounded in years of industrial experience and, unfortunately, technological limitations. For most practitioners, it's easy to fall back on habit than it is to change. For those who have used tuning software, the combination of cost and the data requirements have provided 2 powerful reasons for sticking with manual tuning methods. Now, with that as a background, Damien will delve into each of these 3 areas in greater detail before getting to the case studies themselves. Damien, the stage is yours.
Thank you. Okay, welcome all. Just to start, I suppose, with the first of the misconceptions. I've been doing this way forever. As you can see from the picture, there's a roll of a dice on the page there, and I suppose it represents there's so many variables in the process. And let's face it, I suppose when we're coming to tuning, it's not because it's reasonably steady, it's because there's a lot of oscillations in your process. There could be some noise, it's very hard to see where the process is. But how do we take all of this information and how do we get to a good control? You know, and there's those things in there that tuning needs a little system understanding, a lot of experience, and loads of intuition from a manual point of view. And they're not always available in each individual, whether it's age of an experience or the complexity of the process. So let's have a look at how manual tuning is approached. And you're probably quite familiar with this P versus I, proportional versus integral chart, and it shows the best case performance in the middle. Now, I suppose you could say, is that the best case? Well, it depends. It depends on where your process is. And, you know, with manual tuning, we move around this chart to try and find the one that works, find the one that we like, you know, and it's not always the bottom right corner really slow and steady because we may want better performance. Normally, we start somewhere with a reasonable P and I, maybe 2P, 0.5 or 1I, and see where it performs. And from there, we have to say, well, do we want it faster or slower, more aggressive or more conservative? And from that, we can choose a change our P and I values. It may be done on intuition, you just know from your site, but it also, you know, you may have some math formulas that you use, you know, some Excel spreadsheet, some charts, something that but it's a conglomeration of all these things that you've picked up over time. But it's trying to find the one that works. You know, is it that one? Is it as aggressive as possible, accept some overshoot, get there to the set point? And these are all choices you have to make to get around your process to find the one. Now, how long is it going to take you? It could take a number of steps to get it from one to the other. So there's a lot of choices to be made on that, you know. So from those choices, we can go on to reason 2. It's saving money. You know, I won't buy the software because it costs money. Yeah, but so I'm going to save the company or save me money by not purchasing the software. But are we actually saving money? How many loop responses would we need to see to understand and then tweak the values to get good control? And did we account for all the variables? From the previous chart, there was 9 different representations, but in most manual tunings can take at least that, if not more, to find the one that works. Working through those, it's difficult to figure out, well, where does this loop sit in my process? And it can cause you to tune it right, but then you will upset your process. So then you have to adjust for your process. All of these things need to be considered when you're tuning. And it costs time, and you can cause upsets in your process, which can cause impacts on production. Again, this is the example of the not saving money by buying the software, because you have to do all these steps. There's 8 steps on that page. Now, well and good if your process is a 2-minute process, but if it's a 2-hour or 2-day process, you've changed your step times from a relatively short period to a very, very long period. It could take hours or weeks to tune a process. And we just clear them out until we finally decide, yes, this is the ideal way we want the process to control, and it's in good control. But as I said, it took us time to get there. That time impacts on people, process, and production. There was 8 steps in the previous process. It could have taken us 2 minutes, or it could have taken us 2 weeks. But during that time, how many times did we upset process? And how much times did we change process to impact production? They may be very subtle changes, but they're all changes and will change and affect the variability of your process. So the third reason, I suppose, is software. It can't do it any better. I'm better than software. And it was valid at one time. We've all seen the Excel spreadsheets or the various different software systems that are out there that were attempting to model real-world data, but the real world isn't always Ziegler notebooks. There's always variability. There's always dynamic processes that change it. Up to now, software couldn't do it better, but ours can. It does it open or closed loop, so whether you're in auto or manual, it will model it. And again, some processes are critical, and you won't be allowed to go to manual, so you must do your step changes in auto. Again, that's not a problem. Our software can detect either mode and work properly. And it doesn't need steady state. Ours is the only software out there with a non-steady state modeling. We can model the software regardless of steady state before or after the step changes. We can see through the process variance and pick up the information. Also with the software, it gives us the information to make good decisions. And it gives us the statistic analysis on it, so that we can say, this is what we did, this is how we did it, this is how we improved it. And that's all means that you can record, remember, and I suppose advertise or justify your change to show this is the way it was, this is the way it is now, and these are the improvements we're getting for it. If we look at our software, we can see the 2 different screens that you see here. On top left corner is the data. We're looking at the trended data there, and we see a very variable process. In the bottom right-hand corner, we see the analysis page of our tuning software with the various different pieces of information. Our composite model here showing process gain, time constant, dead time, our closed basically shows us how the process is and will be or can be controlled and the various different parameters that we do it. But if we zoom in now into this and you're looking at non-steady state there, just to give you some context, the red here is the set point, the green in the background there is the process variable, and the green on the lower section is our output. The blue is the model. The blue is the software's mathematical interpretation of the real-world data, and more importantly, it shows the accuracy of the data, or the accuracy of the model by the lack of visibility to the real-world data underneath. From that model, we can then decide how we want to control our process, and we can see over here in the bottom right is on the analysis page of the Loop Pro. We can see the black is the current control, and the green is the proposed control. And as you would choose to go aggressive or conservative, you can change that, the proposed control, to find where you want to control your software. Also with it, we get this analysis to show the recommended control and the existing control and the difference between the two in stability, in settling time, percentage overshoot, amount of output travel, and the last column there is integrated average absolute error, which is the amount of error we've had over time. So they're all very important parameters or reflections of what the model has given us and how we get what we get from it. So with the software, say, okay, so well, prove it to me. How do we know it works? So let's go through some of the case studies. We've got 4 case studies here from a cogen system in the University of Alaska, Haverhill Chemicals, which is an overhead tower pressure controls. We have an electric desuperheater temperature and steam control system, and on the oil and gas industry, there's a platform gas preheater. So let's just talk through a few of these to get some insight into how they used our software and used it to success. So this one is a good example of we've been doing it this way forever. By the way, as I said, that's not a test rig in the university in the labs. This is their cogen facility that they're using to cogen for the campus. So it's quite an intensive process. It shows here the very oscillatory nature of the VFD, and it was constantly hunting to maintain control. We see was very much traveling up and down or cycling to try and maintain that control. And good control is not always fast and aggressive. Good control needs to do what is needed when it's needed, and getting a good model will give you that decision. And we see here from the result, we radically reduced the amount of control for no huge decay in performance. In fact, you could argue that there's an improved performance on it over time. And it means much less wear on your equipment, much less wear on your process, much less variability on it. And again, that's a real key to it, is that that's money saved over time. When you're looking for return on investment or ROI on these kind of things, these are all things that count into that. Next one here is saving by not buying software. So you can see here on this one is maintaining this was the overhead distillation pressure on the plant's main tower, and it was very difficult to maintain this pressure. They actually had like a 20% variability on the process, and it resulted in both incomplete reactions and the loss of production material, because every time this process got to about 60%, it would dump, and the valve position would go to about 60%, it would dump its overpressure, as it was the margin of error on the safety system that they were doing, and it was causing it. And you can see there that there's peaks coming up to 60% and causing dips and variance on the process. When they tuned it, they went from that to this. So it's a marked improvement on the process, and we can see that they had a much more stable process, much more stable overhead pressure, which meant there was a much better throughput of quality product, and improved downstream, because the downstream wasn't seeing those spikes. In fact, their process variance went from 20% to 1%, which is a huge change in a process variance. Reason 3, software can't do it better anyway. So again, on simple systems, you're right, software can't do it any better, but on simple systems, they're very quick to tune, very easy. But on a more complex or a much faster or variable process, it's very hard to do them manually. It's very hard, I should really say impossible. This one shows that there's a 10 to 12 degree variance in the process, and it was constant variance. They could not gain control. They were trying all their tricks to gain control, and it was just getting varying degrees of worse, I suppose. Using the modeling software, they went to this kind of control. And again, if you remember back to the chart on the non-steady state model, very easy for our software to capture that data and model it accurately. They went to this mode, and you can see from the statistics on the improvements, they went from from 4 hours to 1 hour of settling time. It settled much quicker. Now again, if your process had an hour of settling time, very hard to model those processes manually. But the software gives you the information and then gives you the statistics out the back to show how it has improved. The overall stability, it was increased by 117%. You're not going to have those numbers in the manual mode, but you can see the improvements between those two models. But the software gives you those statistics to see what the improvement is, to demonstrate and to justify your modeling, your step changes, to prove the performance of it. We know our software works. We know you get results from it. The last one we have is a software one. Software can't do it any better. Yes, it can. This is a temperature control on the platform gaps on the preheaters. So there was huge variability on it, and if they had constantly cycling the temperature, constantly cycle the moisture content, which meant downstream combustion processes saw this variance and struggled with it. They went from that mode to that mode, and you can see the difference in the variance. Now, you can go, so they gained control on their variance, but they also had the ability then to consider reducing the amount of energy required to maintain that position, as they could move up or down the process variance to be tighter to the constraints or to operate, because there was a constraint further up the process. So you can see from that the different improvements that can be gained from the software, but also the tracking and recording the information from very focused models to very specific information, and then the solutions out of the back of the modeling. I suppose, don't take our word for it. Again, these are well-known companies, and there's some of their quotes from using the software on the first time. And I suppose the takeaways of those are the last sentence on each one. I suppose, truly impressed. This software works magic, and considerable savings for our platform operations. These are the things that our software is a real game changer from a tuning point of view. Again, I've done this forever as an automation engineer, but I've been truly impressed by your software. It really works. I really love the one, this software works magic. You know, this is the black art of tuning. Everybody is afraid to play with it because it's work and don't touch it, or it's so. But our software allows us to analyze it, understand it, and improve the model, to improve the tuning, to improve the process. And you know, it's all about the bottom line and considerable savings to platform operations. And it doesn't matter whether you're a small operation or a large operation, and you're in production either 8 hours a day or 24 hours a day. The costs of production are quantifiable, and when you can define the improvements and show the savings, they really add up to ROI, and it's a very no-brainer almost on the decision making on it. That's pretty much the end of my presentation. I'll open it up to the floor there if you have any questions on it. Feel free to send on a mail. The mail information will be on the next few screens. But as I said, any questions out there?
Thank you for the presentation there, Damien. That was great. You really covered the three misconceptions and demonstrated how innovations in technology, specifically PID modeling and tuning software, have overcome significant hurdles and are now allowing practitioners to optimize loops that were previously overwhelming from a manual standpoint. While we're waiting for more questions to come in, one was raised from our audience, which was, how does non-steady state work? That was something that you referenced in your presentation earlier, Damien. If you wouldn't mind sharing your thoughts on non-steady state.
Sure. Non-steady state is ours. I suppose it's a secret, I suppose. So, and I'm not, I suppose I'm being somewhat glib, but our software has the ability to look through the noise and the process data, which other software cannot do. Our software very accurately picks out the response to the step change, whether it's in auto or manual, and analyzes it, can figure out what is processed and what is non-processed. So it understands, or it can model that software the step change very accurately. It's our key thing. It's just what makes our software so good, so much better than. I suppose the human eye can see it, but our software has figured out how to electronically see it.
Okay. Another question that came in, this kind of gets to the heart of tuning, whether manually or with the help of software, but the question was, how big a step or a bump is typically required when testing process dynamics?
Let nobody tell you any different, that you cannot model PIDs without a step change. A lot of people talk about auto tuners and how they work great, but auto tuners tend to be on very linear processes, VFDs, etc. And they do bump tests, I suppose, but very small bump tests. But that again in VFDs where the response is very linear. For normal process, real world, temperature, flow, pressure, pH, the step needs to be large enough for the software to see the change, to see the response. Now, what number is that? Somewhere between 4 and 6 times process noise. Process noise is the normal variance on the trend, that when you're in constant continuous mode, that there's a continual noise, and it's not electrical noise, it's process noise. It can be just the variance on your process. So it is actually relatively a small number, but 4 to 6 times. Typically on temperature, it could be something like between 0.5 degree and 4 degrees, as in they would be typical bump steps. So I mean, they're not huge changes that you would do on a 50 to 100 degree temperature controlled system, that you would have a bump of between 2 and 4 degrees, maybe.
And one last one that came in just recently was cost. This is a question that is always a little bit sticky, but Damien, can you share some thoughts on cost of software?
Sure. Look, it's a terrible, another tough answer, but how long is a piece of string? Every piece of software is specific to your location, so it's unfair to give an answer to that, other than I talked about it earlier on about the return on investment. This software will pay for itself in very short periods of time. We've had customers that the purchase of software has been paid for in an hour, not even a week, I suppose, in that the first time they used it, they improved their process that had that problem that was there since day one. It will save your commissioning time. It will save your shutdown time. It saves in all places. The ROI is very, very achievable and very quick, and it's much higher than industry standard or expectation on software costs. Let us know what your specific requirements are, and we'll give you a very specific price. I hope that kind of answers your question.
Well, that's a great answer. If there are other questions from the audience, please feel free again to use the chat function. Damien and I will monitor that for just another minute or two. Relative to that cost answer, Damien, one thing I sensed you were getting at was the difference of whether site licenses or single seat licenses, whether you have a specific DCS or you have multiple controllers. Are those all factors that are taken into the licensing consideration, the pricing discussion?
Absolutely. And it's very much, we've tried to model it around to have all needs catered for. As you say, Dennis, whether it's a single point, single use license to a large site that has multiple locations where you want to operate the software from one end of the plant to the other on your current view system, your current SCADA system, or your current, interrogation system. So they're all different needs, different requirements, I suppose. But as I said, we have a model or a variant of it to suit whatever your requirements are.
Great. Well, we have not received other questions. So at this point, Damien and I both thank you for the opportunity to host you this morning for our presentation. We hope you found the information helpful and encourage you to join us for future WebExes. Find them on the Control Station YouTube channel and other great information on controlstation.com. So with that, we'll both sign off and wish you a wonderful day.